Hello everybody. It's Friday, November 7th. This is the third and final baby lecture. So make sure you're comfortable, have a pencil and a paper ready, have your calculators out, and sit with a friend if you like. Be ready to answer some questions. So what you're going to see in this video, in the first part, we're going to look at chi-square tests once more. So I'm going to give you some example scenarios and you're going to do some calculations, quite similar to the kinds of calculations you might expect to see on the midterm and on the final. For the second half, the new stuff, we're going to look at inferences for regression. So if you've seen baby lecture number 2, in there I reviewed some of the concepts of linear regression that you would have learned in 2208. So here in the second half of this video, we're going to look at some new ideas. So before we start looking at the chi-squared scenarios, let's just review once more the 3 chi-square tests that we learned. So the first one is a goodness of fit test. The way to recognize when this scenario requires a goodness of fit test is you need to see that there is one categorical variable and there's a sample drawn from a single population. Next, we did the homogeneity test, and so there, it's one categorical variable again, but in this case, there's 2 or more populations. And then lastly, we did the independence test, where you have 2 categorical variables drawn, where samples are drawn from a single population. So you might want to sketch these down for reference, because in the next 2 scenarios I'm going to show you, you're going to need to guess which scenario it is. So you might write down the name of each of these tests and just write down the number of variables and the number of populations from which data is drawn. And while you're doing that, let me just emphasize that when you have a goodness of fit test, the data appears in the form of a frequency table. So that is, it's a table with a single column. And the reason it has a single column is because you have only one categorical variable and you have one population. Homogeneity tests and independence tests, in those cases, the data appears in a contingency table. And so that's one of the big differences. Interestingly, in both the homogeneity test and independence test, when you calculate those expected values, the calculations are exactly the same. In fact, all of the calculations are the same. The calculation of expectations and the calculation of your chi-squared test statistic, it's actually the same for homogeneity tests and for independence tests. And that's because both of those tests give you data in the form of a contingency table. So the difference between those 2 tests is about it's about what is being asked. It's the null and alternative hypotheses. Okay, so let's just look at an example. So here we're imagining there's an insurance company, and it's going to collect data from a random sample of cars that they insure, which were involved in some kind of accident. And their objective was to determine whether the kind of accident depends on the color of the car. So take a moment, maybe pause the video if you like, and think about which of these 3 chi-squared tests we should be using in this scenario. So hopefully you recognize a couple of things. First of all, in this scenario, we have the word depends. Right? We want to determine whether the kind of accident depends on the color of the car. So that gives you some hint that it's probably a chi-square test of independence. But to be sure, we need to see that there are 2 categorical variables and that the sample is drawn from one population. So do we have 2 categorical variables here? Well, we do, because we're looking at the kind of accident, so that's one category, and the color of the car, that's another category. So 2 categorical variables, and the population would be all of the cars that the company insures. We're taking a random sample of, I guess it's going to be, as you will see, it's going to be 200. So we're taking a random sample from a single population of all the cars that the company insures. So indeed, it's a independence test. So we have category 1, categorical variable 1, I should say, is car color, and categorical variable number 2 is car type. Yeah, I don't like the way I said that, so I'm going to go back in and just change that. So let's say categorical variable 1 and categorical variable 2. Yeah, the reason I did that is because we need to distinguish between a categorical variable and the actual categories. So let me just make that clear. So categorical variable, I forgot the numbers. Categorical variable 1 is car color. Car color has 4 categories. As we will see, there's going to be black, white, blue, and red. And categorical variable 2 is accident type, and as you will see, we're going to have 3 accident types. So we want to make a distinction between what we call a categorical variable and the number of categories each variable has. Right? So just to make that clear. So I was going to ask you to state the null and alternative hypotheses, but you've probably seen them already, so let's just look at those. So the null hypothesis is that car color and accident type are independent categorical variables. The alternative is that they are not independent, or in other words, that they are dependent, or you could say that they are associated. Okay, so we're going to look at some actual numbers in a minute, but before we do, I want to remind you of something that you learned in 2208. So in that course, you might have been presented with bar graphs like this, and you'll be asked something like, does there appear to be evidence that the distribution across accident type depends on car color? Another way you might have been asked the question is, does it appear that the 2 categorical variables are associated or dependent? And so looking at these, yeah, I wonder what most of you would say. So in Math 2208, you were told that if bar charts look different, then that is evidence that the 2 categorical variables are dependent. And so here it's true that the first 3 charts, the first 3 bar charts, are for cars of color black, white, and blue. They look more or less the same, like just with minor differences, but the bar chart, or in other words, the distribution across accident types for red cars looks very different than the rest. And so in Math 2208, presented with a graph like this, you would have been correct to say that it appears that the distribution across accident type depends on car color. And that's because the distribution for red cars looks quite different from the rest. And so the difference between what you learned then and what you're learning now is now we can actually put what we're seeing just by observation to test, and we can actually get a number, we can get a p-value, we can subject our visual impression of the data, and the conclusion that we're drawing here is that there is a dependency. We can put that to a rigorous test. So we'll get to that. We'll return to this at the end. So let's look at the data. So here we have a table. This is a table that would come from Minitab. This is a table very much like what you would see on the midterm or final. So you can see we have a bunch of numbers, we have some numbers covered up, and you're going to be required to fill in the values of those missing numbers. So let's just make sure you know exactly what we're looking at. So first of all, across the top we have the first categorical variable, the car color. So we have 4 categories there. And along the left-hand side, we have the second categorical variable, the accident type. We have 3 categories there. Notice on the margins of the table, we have our totals, and down in the bottom corner, we have our grand total, 268. Now, each contingency has displayed in this table 3 numbers. What do I mean by contingency? Well, if you pick one car color and one accident type, together, those form a contingency. So for example, if we pick fender bender and red car, we can see the contingency in this box is showing 3 numbers. The top number is the observed count. That comes from the data. The second number is what we would expect to see if the null hypothesis was true. And the third number is the contribution to the chi-squared statistic. Now you know how to calculate all of these numbers. And so what I would like you to do is pause the video, take 10 or 15 minutes, go through your notes if you need to, and calculate a value for each of these 5 letters, for each of these boxes. If you get stuck on any one of those, just let it go and go to the next one. I don't want to make this a painful exercise, but I want you to have a little bit of practice in calculations, and if it makes you go back and review your notes a little bit, that's fine. So pause the video now, take as much time as you need to fill in these missing values, and I'll see you in a minute. Okay, welcome back. I hope you managed to get at least some of these calculations. Let's have a look. In the first case, we're looking at the contingency, a white car, and the accident type is a door dent. And you can see of those three numbers, the one that's covered is the first one. So that is a count. That is an observation. And so how do we figure out what the count is for that contingency? Well, we know that if we add across that top row, we know that the total is going to be 92. And so all we need to do is take 92 and subtract the numbers we see, and we get the number that's missing. So it's 28. So that calculation is fairly straightforward. For the contingency blue car with a door dent, you can see that the missing number is the one on the bottom. It's the bottom of the three numbers. That would be a contribution to the chi-squared statistic. And so what you had to remember is to calculate the chi-squared statistic contribution. You look at the deviance between what was observed and what you would expect to see if the null was true. You square that, and then you divide again by the expectation. And so if you do that calculation, you'll get 0.2604. So in the next case, we're looking at the contingency, a white car. The accident type is fender bender. You can see it's the second number that is covered up. That second number is the expectation, assuming the null is true. To calculate expectations, we need to look at the column total, the row total, and the grand total. And so here we take the column total, which in this case is 76. We divide by the total sample size, 268, and we multiply by the row total, which is 115, and we get 32.61. For part T, again, we're in the contingency. Okay, the contingency is a black car. The accident type is collision, and you can see that we're covering up the third of those three numbers. That third number is the contribution to the chi-squared statistic. And so again, we're just comparing what we observed with what we would expect to see if the null was true. And so we calculate that deviance, square it, divide by expectation again, and here we get 0.6081. And finally for E, and for this contingency, it's a blue car. The collision type, the accident type is collision. And here again, we're looking at the middle number, which is the expected value, assuming the null to be true. So we're looking at the row total, the column total, and the grand total. And so performing that calculation, we get an expected value of 14.34. So you can see these calculations are not that difficult. You just need to remember which expression to use to perform the calculation. So essentially, you need to remember the top number is what was observed, the middle number is what you would expect to see if the null is true, and the bottom number is the contribution to the chi-squared statistic. So these should be easy points on a midterm or final, with a little bit of practice, of course. Okay, so next let's talk about the conditions. So here, maybe you can take a moment, pause the video, take a moment, and state the conditions which must be satisfied to carry out the chi-squared test, and then answer whether these conditions are indeed satisfied. Take a few minutes to jot those down, and then I'll see you on the other side. Okay, so those conditions are, first, you have to have two categorical variables. It's an independence test, and we're asking to see whether these two categorical variables are independent or not. So we have to have two of them. The samples are drawn from a single population. Of course, it has to be a random sample. That gives us the independence. And then perhaps the most important of the conditions is the expectation. The expectations or expected counts must all be 5 or more. And if you look at the previous table, we can see that that indeed is the case. So all of these conditions are satisfied. Okay, next question. Right, what is the degrees of freedom of the chi-squared statistic in this case? And what is the critical value for a 5% test? I think here again, let's pause the video, take a few minutes to figure out the degrees of freedom, and then look up the critical value for a 5% test. Okay, so the thing to remember is we have a contingency table. The degrees of freedom for that contingency table is the number of rows minus 1 times the number of columns minus 1. So in this case, the rows would be the three categories of accident type. So we have 3 rows. for the 3 different accident types, and the columns would be those 4 colors. So we have 3 rows, 4 columns. 3 minus 1 is 2, 4 minus 1 is 3, 2 times 3 is 6. So we're looking at 6 degrees of freedom. And for a 5% test, we can see at the top of the table 0.05. That gives us a critical value of 12.592. So we can make a quick sketch, and we can say that our decision rule is that we will reject the null hypothesis at the 5% level of significance if our test statistic is greater than the critical value 12.592. Next question. Given a table like this one, how would you go about calculating the test statistic? Yeah, I'm just pausing for a second to give you a moment to think. Right, so I'll tell you this, you won't have to do the calculation yourself, but you have to know where the calculation comes from. So to calculate the test statistic, you can see that for each contingency, we have a contribution to the chi-squared statistic. That's the third number within each contingency. If you add all those numbers together, you will get the chi-squared statistic. So again, we're never going to make you sit and add a whole bunch of numbers together because that's just tedious. But you do need to understand how to get the chi-squared statistic from a table like this one. Okay, now here's an example of some Minitab output. And here the question is going to be, what is the value of the chi-squared test statistic in this case? And what is its approximate p-value? Maybe this is a good time to pause the video again, take a few minutes to answer this question. Right, so one of the points of doing this exercise for this slide is you will probably be shown a chi-squared table like this one where there's more than one test statistic, and you need to know that the test statistic that we talk about is the first one. It's the Pearson chi-squared statistic. So here our test statistic is 9.404. And if you look at the table, you can see 9.404 is less than 10.645. We're looking at 6 degrees of freedom. And so what does that tell you about the p-value? Well, this is the way I like to think about it, in case you weren't sure. If our test statistic was 10.645, then the area in the upper tail of the chi-square distribution, which is what the p-value would be if that was our test statistic, that area is 10%. But because our test statistic is to the left, the area in the upper tail is more than 10%. So our p-value is greater than 10%. Okay, here we're going to ask, what can we conclude testing at the 5% level of significance? So just as an exercise, just pause the video, write down what you need to say about the significance and strength of the test in this case. So the significance, the p-value is greater than 0.05, so we cannot reject the null hypothesis at the 5% level of significance. And for the strength, there is no evidence against the null hypothesis that car color and accident type are independent. And why is that? Why do we say no evidence? Because the p-value is 0.152. And where does that fall on our table? It falls in that first category on the bottom. A p-value greater than 10% indicates no evidence against the null hypothesis. Okay, so now let's go back to that I always forget what these things are called. This is a bar chart. So we're looking at the bar charts. So here we have, basically what we're looking at is the distribution, the sample distributions across accident type for each of the 4 colors of car. And so what we said in the very beginning is if we were just following with what we learned in Math 2208, and we were asked whether or not these 2 categorical variables are associated or dependent, we would conclude that they look like they're dependent because even though the first 3 bar charts look more or less the same, the bar chart for red looks very different. In other words, the distribution across those accident types looks like it depends on which color the car is. If you're a red car, you have one distribution, and if you're black, white, or blue, you have a different distribution, right? So it looks like there's a dependency. However, the question is, are the differences that we see in these bar charts, are those differences systematic, or are they just a matter of sampling variability? And looking at this, I would have guessed the differences are systematic. It looks to me like the distribution across the three across the three accident types. It looks to me like that distribution for red is different than the other three, systematically different. However, we did the chi-square test and we failed to reject the null hypothesis. And so we found no evidence to conclude that there is a dependency. So since we failed to reject the null, we can conclude that the differences that we can see in these 4 bar charts are due to sampling variability alone. In other words, they are random, not systematic. Right? So our test is telling us that there's no evidence of a systematic difference in these 4 distributions. The differences we see could easily be due to just sampling variability. So I think that's very interesting, because if you were studying 2208, you would give one answer. You would say that these 2 categorical variables are dependent. But now in 2209, now that we can put that claim to a rigorous test, we find out, in fact, that's not the case. So I think that's quite interesting. Okay, so let's do one more, a shorter example of a chi-square test. Oh yes. Oh, before we do, yes. Okay, before we do, let's pretend. Let's treat this slide as a quiz. What I'd like you to do is pause the video, and for each of these 3 chi-square tests, write down the conditions under which you would conduct that test. In other words, indicate the number of variables, the number of categorical variables, and the number of populations from which samples are drawn. So try not to look at your notes. Just see what you can remember. Just from memory, just write down those conditions. Just pause the video and take a few minutes to do that. Okay, so I hope you put yourself to the test. That's a good way to facilitate your learning process. So goodness of fit test again is one random variable, one categorical random variable, one population, a sample drawn from one population. Homogeneity test is one variable, 2 or more populations. And the independence test is 2 variables and 1 population. Right, so it's important that you can distinguish one of these cases from another. On the midterm, probably and most certainly on the final, you'll be given scenarios, and you have to figure out which of the models that you'll be learning in this course apply to which of those scenarios. So it's really important that you can distinguish between these 3 scenarios. Having said that, here's another scenario, and I want you to think about what kind of chi-square test applies in this case. So here we're imagining that a car manufacturer collected a random sample of 200 warranty claims filed over the past 2 years to test whether claims are uniformly distributed across days of the work week. So take a moment and think about what kind of test you would be conducting here. So let's dig into this. So first of all, notice that in the data, a couple things to notice. First of all, what kind of table is this? This is not a contingency table. This is a frequency table, because you have one list of categories for a single categorical variable. And next to that, you have your actual observations. And so the first 2 columns of this table, that's just a simple frequency table. So that's telling you something. That's telling you that we're probably looking at, what is it? We're probably looking at a goodness of fit test, right? Okay. And so what are we being asked here? Remember, for a goodness of fit test, you're comparing an observed distribution of counts from your data with what you would expect to see under a given null hypothesis. In this case, the null hypothesis is that the distribution is uniform. So what we're saying, let me just paint the picture a little bit more clearly here. So imagine we have a factory, and in this factory they make cars, and they work from Monday to Friday. So some cars are going to be made on Monday, and some cars are going to be made on Tuesday, and so on and so on. So of all the cars that are made, that's the population, some of those cars are going to have things wrong with them. So when someone buys the car, they discover something's wrong, they make a warranty claim, and then the manufacturer is responsible for getting that thing fixed. And so here what we're saying is, in a random sample of 200, here we have the observed warranty claims according to the day of the week that the car was made. Under the null hypothesis, that distribution is uniform, which means that the proportion is equal for all 5 days of the week. So that's going to be 20% for each day of the week. In a sample size of 200, 20% of 200 is 40. So the expected counts for each of those days of the week under the null hypothesis is 40. And that's going to be compared with what we observed. Okay, so that's the scenario. So we're looking at a chi-square goodness of fit test. The category is days of the week, and we're counting warranty claims for each day of the week. The null hypothesis is that the observed values are consistent with a uniform distribution. In other words, with equal probabilities for all 5 days of the work week. Another way of saying it is that the null hypothesis is that the population distribution is uniform. So we can use that as our null. The population distribution is either uniform, or if we reject that, we can conclude that it is not uniform. Okay, so goodness of fit test. Pause the video here, figure out what the degrees of freedom is, and look up the critical value for the test. Just pause the video now, take a moment. Okay, so for a goodness of fit test, the degrees of freedom is just the number of categories minus 1. So here we had 5 categories, Monday to Friday. 5 minus 1 is 4. So we're looking at 4 degrees of freedom. And if we are to conduct a 5% test, the critical value is 9.488. So, having said that, now let's go back to the table. Looking at this table, looking at the contributions to the chi-square, which is the last column of the table, what can we conclude? Are we going to reject or not? So what you should notice, if I just go back a slide, remembering that the critical value for our test was 9.488. And so if our test statistic is bigger than that number, we're going to reject the null hypothesis. And if you look at that last column, the bottom number is more than 9, and the top number is 6. So if you add those together, you're going to get a number bigger than the critical value. So we reject the null hypothesis that the probability of a warranty claim is the same for all days of the work week because the test statistic is greater than the critical value. And we're rejecting at the 5% level of significance. Okay, so all of this, fairly routine. There's going to be one last part that I want to talk about. So you're not going to be asked to look at a table like this and make some kind of interesting observation. But if you do so, I can give you bonus points on your midterm or final. In this particular case, just to give you an example of the kinds of interesting observations that you might see, you'll notice that so first of all, we rejected the null hypothesis. What does that tell us? That tells us that the probability that a car manufactured car later gets a warranty claim, it depends on the day of the week. In other words, that probability is different depending on the day of the week. The distribution is not uniform. So look at Monday. We can see that the observed counts, so in a sample of 200, in a sample size of 200 cars with warranty claims, we can see that we observed 56 were made on Monday, whereas we would expect to see only 40 on average if the null was true. And so we're seeing more than what we would expect to see on Monday. If you look at Tuesday, Wednesday, Thursday, the expectations are very similar to what was observed. But then again, on Friday, you can see that we only saw 21 cars that with a warranty claims were manufactured on Friday versus an expectation of 40 if the null is true. So we're seeing less than what we would expect to see if the null is true. So both Monday and Friday, those are the observations that are causing us to reject the null hypothesis. And so what might we conclude as sort of an interesting observation? We can see on Monday the number of claims is higher than expected under the null, and on Friday it is lower than expected. This suggests that the workers who make the cars tend to make more errors than average on Monday and less errors than average on Friday. Interesting result. So if you're given a case, some kind of chi-square test, and you're given a table and you can look at the individual observations, you can compare them with expectations, you can see how much those observations contribute to the chi-squared statistic. If you see any interesting pattern, then you can say, write a few sentences about it, and that will be worth some bonus points on the midterm or final. Okay. So that is it. Now, that's the first half of the lecture. Now we're going to go into inferences for regression. So this part of the lecture, there's not going to be really much for you to calculate. You can just sit back and listen. It's going to, at first, this stuff is going to look a little bit theoretical. So I'll just put that out there as sort of a warning. Once I see you again in class, we'll be doing some more concrete calculations. So I just want you to open your mind and just take a deep breath. Get ready for some theory. I am absolutely certain you can understand all the things I'm about to say, but it is going to be a little bit abstract in places. So just be prepared for that. So starting with something concrete at least, here is the scenario that we're going to look at. So first to say, a chess player must work hard to gain playing strength. The question is there an easier way to become better at chess? In one study, 50 players with an online chess rating between 2100 and 2200 were randomly selected to participate. The players were instructed to halt all chess training apart from watching game reviews posted on YouTube by a popular chess personality. The objective was to determine whether watching game reviews alone was enough to improve a player's rating. So that's this scenario. So basically, just to say it in a more simple way, a player is going to watch some number of hours of chess videos, and then we're going to measure how much their playing strength has changed in response to those watching hours. And so here is the pretend data. You can see that there's, well, you can't see that, but trust me, there's 50 dots. Each of these dots represents one individual who participated in the study. On the horizontal axis, we see the viewing hours. So that's the number of hours they spent looking at chess videos on YouTube. The vertical axis is the change in their playing strength, the change in their rating. And so what can we see in this data? In this data cloud, if you will? We can see there's a positive trend. And the positive trend looks more or less linear. And so that's the first thing that we need to see. If we're going to use a linear regression model, in the scatter plot of the predictor variable versus response of the x versus y, we need to see that it looks like there's a linear trend in that data cloud. Here, that is the case. So the linear regression is using linear regression, we're going to get a line of best fit. We're going to get fitted values, the y-hats, and that line of best fit is going to have an estimated intercept, that's the b0, and an estimated slope, that's the b1. And the whole objective here is, the point here is that these model coefficients, we call them model coefficients, b0 and b1 are called model coefficients. They are estimates that come from the sample. What is it that we're estimating? We're estimating population values, corresponding population values. So that's the abstract part that I'm about to get into. So this is the formal regression model. So I'm going to take you through and explain all the parts of this model. And so after a few slides, once we get to the end of this, it's going to seem pretty straightforward, I hope. Right now, it probably looks a little bit weird because you're not seeing B0, you're seeing the Greek letter beta 0. You're not seeing B1, you're seeing the Greek letter beta 1. And also you have this E on the end. So let's just see what all of these things mean. So first we have a Y variable. That's the response. It's also called the dependent random variable. Here we have the X variable. That's called the predictor or the independent random variable. So in our case, the predictor is the number of hours a person watches these chess videos. The response is the change in their chess playing strength or their chess rating. So now let's look at the model parameters. We have two of them. We have a population intercept, right? So up until now, when we talked about regression in 2208 and in the last lecture, we used B0 for the intercept. B0 is an estimate that comes from data. What is it estimating? It's estimating a population intercept, an unknown population intercept. Likewise, there's beta 1. That's a population slope estimated by B1. So beta 0 is estimated by B0, beta 1 by B1. Beta 0 is a population intercept. Beta 1 is a population slope. These are unknown, and we estimate them from data. So what else can we say about the model? Well, we can think of the model in terms of components. And so our response is composed of two things added together. First, there's a systematic component, and that represents the population mean response. So this is a term we're going to hear a lot. Population mean response at a given value of x. Next to that, there's a random component. That random component is due to individual differences. So what the systematic component tells us is if I tell you how many hours of study if I tell how many hours a person watches these chess YouTube videos, and if we knew what our population parameters were, the population intercept and the population slope, then you could calculate what you would expect to see as an average change in the chess playing strength. That would be a systematic change in chess playing strength due to the number of hours a person spends watching the chess videos. That's the systematic component. The random component is due to individual differences because, you know, if one person watches, say, 50 hours of chess videos, their chess playing strength would change by some number. If another person watches the same 50 hours, their chess playing strength would change by a different value. Why? Because of individual differences. So those individual differences are taken up by this random component. Okay, so let's make this a little bit more concrete. So imagine that we have several participants in this study who spent 50 hours watching chess videos. So we're looking at 50 hours as our predictor variable, and we're going to predict the population mean response. Well, in fact, if we actually have the population parameters, we can calculate the exact population mean response. And so what's the symbol for that population mean response? We use mu, because mu is a symbol for population mean. We put a little y in the bottom corner to remind ourselves that this is a mean response in a regression scenario. And then in brackets there you see the 50. That just indicates what the value for x is. So this round circle here represents the population mean response for participants who spend 50 hours watching chess videos. That mean response, of course, is the change in their chess playing strength or chess rating after those 50 hours of watching videos. Now here's the point. If we have a whole bunch of people who spend 50 hours watching videos, we don't expect all of them to have the exact same response. We expect some variation due to individual differences. So somebody might be there, or there, or there, or there, and so on. So this could be the actual individuals, and those individuals are sort of, if you look at the scatter of those data points, they're more or less centered at the population mean response. And again, we could calculate the population mean response if we knew beta 0 and beta 1, those population parameters. But the point is, there's going to be scatter around that population mean response, and that scatter is due to individual differences. So the point is, individual responses will vary. And so how do we account for that? So here, this is the same diagram, but now I'm just saying x instead of any particular number of hours. I'm just saying x, some number of hours. We have a population mean response for that number of hours. We have a population mean response, which could be calculated exactly if we had population parameters, but of course we don't. But that's the model. Okay, that's the way we model the process. And we also have our individual responses. And how do we get those? We take the population mean response, and for each individual, we add a random error. That random error is due to individual differences. So each individual blue dot representing a different person would have a different random error. So you can see the response y has a systematic component and a random component. The random component takes into account individual differences. Now, a key idea here is that the distribution of the response that distribution, although it's centered at the population mean, it has variation, and that variation is consistent with the normal distribution. So in other words, the individual measurements for any value of the predictor variable are assumed to follow a normal distribution with some amount of spread as measured by standard deviation. And so these individual measurements are approximately normal in distribution. They're centered at the population mean response, and they have some variance which is given by a population standard deviation. And it's the standard deviation of these individual differences. You can call them errors. When we actually look at data, we can estimate what those are using the residuals. And that's why we use the same symbol E. So that's sort of the big theoretical picture of what's going on. So I'm going to talk about this again when I see you next in class, and probably once or twice more, just to try to help you get a good handle on the concept. But let's here just sort of summarize it overall. So here's the big point. At any value of x, the predictor variable, the response y, the response variable y, is assumed to follow a normal distribution centered at the population mean response, which is the systematic component of the model, and with variation due to individual differences, which is the random component of the model, right? So we have the population mean response represents systematic differences in our response due to differences in the predictor. So in our situation, in our scenario, it represents systematic differences in the change in playing strength due to differences in the number of hours a person watched these videos. And then down here, this E represents random effect due to individual differences. It has a population standard deviation. That's also a population parameter. Okay, so that is the abstract theoretical part. And that's it. That's the only abstract. I think that's pretty much all of it for regression. So now we're going to get into something a little bit more concrete. We're going to look at some numbers. So first of all, here we have that same data. The red line is the regression line. The green dashed lines represent a confidence envelope. So that's something new. So at each value of x, we have the red regression line is the modeled mean response, right? So the y hat with B0 and B1, of course, this is an approximation of the actual model, which is beta 0 plus beta 1x. This is our approximation. So this is basically our best estimate. A best estimate of the population mean response for different values of x. That's the red line. The green dashed lines indicate a 95% confidence interval for the population mean response. So let's just get into that a little bit more. What you're looking at here is an example of Minitab output. So on top, you can see here, this is our regression line. So 0.85 is our estimate of the intercept. 0.5415 is our estimate of the slope. Viewing hours, that's our x variable, that's our predictor, and rating change is our response, that's the y value. Okay, so what we're going to look at here is at 50 hours. So at 50 hours, there is a predicted population mean response, which is right there on the line. So that predicted population mean response is 27.9283. That's the modeled mean response for a person who watches 50 hours of chess videos. So that's our estimate of the population mean response, of the actual population mean response. What is the confidence interval for the population mean response? Here we have a 95% confidence interval for that population mean response when x is 50 hours. And you can see how that's represented on the graph. So any value of our predictor has a corresponding 95% interval in this case, which is represented on the graph by these green dashed lines. Okay, so now we talk about making inferences. Things are going to get even more concrete now. We have population parameters, as I mentioned. So beta 0 is the population intercept, beta 1 the population slope. The sigma with the little e in the corner is a population standard deviation for the random component of the model due to individual differences. The primary objective is to make inferences about the population slope, which is the beta 1. And we can do that in two ways. We can construct a confidence interval, or we can conduct a hypothesis test, typically where the null hypothesis is that beta 1 is equal to 0. The question is, looking at our two quantitative random variables, our x and our y, is there evidence of an association? If there's no association, we would expect to see that the population slope is 0. If there is an association, we would expect to see evidence that the population slope is not 0. And so that's why, as a null hypothesis, beta 1 equal to 0, that's the typical null hypothesis. Right, so now, these tests are actually very easy, much, much easier than when we looked at t-tests, like a 2-sample t-test, a 1-sample t-test, a paired t-test. Those calculations are a bit more complicated because we always have to calculate what the standard error is. In this scenario, you're going to be given standard errors in a table. So before we get to that, the population parameters, beta 0, beta 1, and sigma sub e, if you will, all three of those are estimated, and you can find them in the Minitab output. Right, so here, the estimate for the intercept from the table is 0.85. B0 equals 0.85. The estimate for the slope, B1, is 0.5415, and the estimate for the standard deviation due to individual differences is given the symbol S, and that's 15.6825. So those can be found in the table. What's also found in the table, this is something that you would have seen in the last lecture, the last video lecture, and that is this R squared. This is the coefficient of determination. Let me just review again what that is or where it comes from. So what we're looking at here is the analysis of variance table for regression. And how do I know this is for regression? Because the first source of variation is called regression. So remember that this first number, this is the sum of squares of y hat, of your fitted values. The second number is the sum of squares of your residual errors. And these two numbers added together add to the total sum of squares, the sum of squares for your observations. And remember that sum of squares is a measure of variation. Now, what do these have to do with the coefficient of determination? Well, it's just this. The coefficient of determination, if you look up at this fraction, the top number, it's 10,103.9. That represents the variation that's been taken up by the fitted values. And on the bottom of the fraction, the 21,909.6, that is the total variation in the y values, in the observations, in the response variable. And so that ratio multiplied by 100 gives us 46.12%, which is exactly what we saw in the Minitab output. And so in other words, the coefficient of determination is the proportion of variation in the what do I call them again? In the response variable, the y value, the response variable, that is explained by differences in the predictor, the x. It's worth remembering that, by the way. Okay, now let's just finish up with a little bit about the inference. So we're going to start with a confidence interval. We're going to construct a 95% confidence interval for the population slope beta 1 from its estimate B1. Now, just to be clear, this is what we're going to see here is a confidence interval for the slope. If I just go back a few slides, don't get that confused with these. So here we're looking at confidence intervals for a population mean response given the value of the predictor, the value of x. That's one thing. That's one place where you'll see confidence intervals. And the other place where you will see them is for the actual population parameters. So where am I now? Right here. Okay, so now the good news is everything we need to calculate the interval is in the table. So remember the form of a confidence interval, we're going to take a point estimate. So B1 is a point estimate for beta 1. And then plus or minus a margin of error. The margin of error has two parts. There's going to be a critical value taken from a t-distribution, and there's going to be a measure of uncertainty. To get the critical value, we need to know the degrees of freedom. So here's something worth remembering. In this kind of regression model, the degrees of freedom for the test statistic, for the critical value, well, for the t-table, let's say, is the sample size minus 2. The reason for that, I would rather explain when I see you in person. So we'll leave that for now. But we'll just remember, for a simple linear regression analysis, the degrees of freedom that you need to do the inferences using a t-table, it's the number of observations minus 2. Okay, so let's have a look at that. So the sample size is 50, so the degrees of freedom is 48. We're going to estimate our critical value using 45 degrees of freedom. If we want a 95% interval, the critical value is 2.014. Okay, so let's make our confidence interval. First, the simplest thing to do is to calculate the margin of error. So we're going to plug in 2.014, that's our critical value. The standard error is given in the table. So you don't have to calculate the standard error, it's already given. So that's nice, that makes this a bit easier, compared to, say, doing a 2-sample t-test. Multiplying those together, we get a margin of error. Now it's simply, we take our point estimate, plus and minus that margin of error, and we get our 95% confidence interval for the population slope. Okay, how do we interpret this interval? I'm just going to give you the interpretation. This time we'll probably talk more about sort of a formulaic way of coming up with the explanation. But here, I'm going to start by saying, assuming the conditions for the central limit theorem and for linear regression are satisfied, I need to include both the central limit theorem and the conditions for linear regression. Because the conditions for linear regression must be satisfied, but also the conditions for the central limit theorem must be satisfied so that we can use a t-distribution. Okay, so assuming all that's the case, we're 95% confident that the population parameter beta 1, and then see the next part, I'm explaining in context what beta 1 means. So we're 95% confident that the population parameter beta 1, which represents the average change in playing strength for each additional hour spent watching chess videos on YouTube. So we're confident, 95% confident, that value is between 0.37 and 0.71. And then to add sort of an interesting observation, because the lower bound of this interval is greater than 0, in other words, the interval is positive, we can infer that beta 1 is not 0, and that watching chess videos on YouTube can improve playing strength on average. Yeah, I think I'm going to change the way I say that to be consistent with what I've been using in class. So I'm going to say because the interval is constant. Let me say it that way. Oh, sorry, I meant to say it's positive. Yeah, let's say it that way. That's the way I've been saying it so far in this course. So there. Okay, so that's the interpretation. Now, just to finish up, we have to look at the other side of the inferential coin. That's the hypothesis test. So you can see here the null hypothesis is that the population mean slope is 0 versus not 0. If the population mean slope is 0, in other words, if we don't reject the null, then we can't say there's an association between our predictor and response. But if we do reject the null hypothesis, so that there really is a non-zero slope, then we can say, yes, there is an association between the predictor and response. So how do we do this calculation? The test statistic is very easy. Like all test statistics, we're comparing what we observed minus what we would expect to see on average if the null was true, and then we divide by a measure of uncertainty. And so in this case, again, everything we need is in the table. Testing at the 5% level of significance. Well, let's get our decision rule before we continue. So again, sample size is 50. Degrees of freedom is sample size minus 2. So we're looking at 45 degrees of freedom as an approximation. We want a two-tailed test with a two-tailed probability of 5%. You can see the critical value is the same as we used for the 95% confidence interval. So here are the hypotheses. This is the distribution of our test statistic, assuming the null is true. We got critical values that put 2.5% into the tails, and there's 95% in the middle. And we're going to reject the null hypothesis if our test statistic is either in the upper tail or in the lower tail. In other words, if the absolute value of our test statistic is bigger than 2.014. And we can see our test statistic is definitely bigger. It's 6.4083. And so we can reject the null hypothesis at the 5% level of significance and conclude that viewing chess videos online has an impact on chess playing strength. In other words, there is an association between sorry. In other words, there is an association between the number of hours spent watching these videos and the playing strength of the player who's watching. Okay, so let's see what is left to say about this. Yeah, okay, so if you look at the complete Minitab output, which I'm showing now here, you can see we have everything. We have our coefficient, standard error of the coefficient. We have our 95% confidence interval for beta 1. And we have our test statistic and p-value for the null hypothesis that beta 1 is equal to 0. Everything is there. You just have to know how to read it. Okay, now the last thing to talk about, the conditions for which linear regression can be performed. So I talked about these conditions in the previous video, so most of this is going to be a review. Of course, the first condition is the predictor and response must be quantitative. But setting that aside, the scatter plot must suggest a linear association. So this we call the linear enough condition. And it's often checked by looking at residuals. And what do we need to see in the residuals? We must see no trend in the residuals. The spread of the y values must be roughly the same for all values of x. So this is called the constant spread condition. Sometimes it's called the, what's it called? What did they call it? They call it the thickening of the plot condition sometimes. I like to call it the constant spread condition because what we want to see is a constant spread. So that's usually also checked by looking at residuals. We'll look at an example of these in a moment. You should see no unusual observations. So observations which have very large residuals or leverage points, if you remember what those are. If we see any such values, we take them out of our analysis. If you don't remember what leverage points are, I suggest you go back and look at your notes for 2208, or you can look in the textbook. If you don't have a copy of the textbook, you have access to an online version. And if push comes to shove, you can ask me in class, and I'll just show you a few pictures to explain it. But I didn't want to explain it here because right now it's not that important. Finally, the residuals themselves, the residual errors, must be approximately normal in distribution. We call this the normality condition. It's checked by looking at the normal probability plot of residuals. So for the current analysis with the chess players looking at videos, whoops, where are we? Here. These are the residual plots. The bottom two plots don't matter that much, so we're going to look at this first one. This is the normal probability plot. Now, this is not a regression plot. It's a normal probability plot, and the only thing you can infer from this plot is whether or not the residuals are consistent with the normal distribution. How can you tell they're consistent? If the data points fall in a straight line. Like beads on a string is what I like to say. If you see that, in this case we see, yes, these blue markers are approximately in a straight line in the normal probability plot, so we can conclude that the residuals are consistent with a normal distribution. So that was one of our conditions of our model. That condition is satisfied. The other plot we want to look at is residuals versus fits. And what do we want to see here? Two things. We want to see that there's no trend in these residuals, in this data cloud of residuals. So here we don't see any trend. Also, we want to see that the spread in the vertical direction is roughly the same as we move from left to right. Here, that is also satisfied. And so we can conclude that the normality condition, the linear enough condition, and the constant spread condition, these are all satisfied in this case. That's all. Bye for now. See you later.